Hello dear subscribers and viewers of this channel. My name is Andriy Severinov, and today we have our second lesson, dedicated to working with the PoligonSoft metal casting simulation system. In the first class, we built a finite element mesh for our casting. Today, we are going to learn how to input the necessary data to perform a simulation of steel casting in a sand mold. We will obtain the calculation results and analyze them. We are going to model the solidification dynamics of our casting, the formation of thermal nodes and the location of defects with macro and micro porosity, and the formation of shrinkage defects on the surface of the part. Let's start. Before me is the startup window of the PoligonSoft system. The second button opens the master preprocessor. We start it. For better visibility, I am going to switch to ribbon interface mode, but you don't have to do it. I press the gear to access the basic settings of the program. There I select ribbon and then OK. The first thing we must do is load the file with the finite element mesh that we prepared in the previous lesson. You can also download the file in the comments of this video. In the main tab, we select Open Geometry. As we can see, meshes created in different mesh generators can be loaded. It is also necessary to specify the units in which the project was made. This is very important, as if incorrect units are indicated, the scale will change and the simulation will be incorrect. Our mesh is made in millimeters using the Solidification mesh generator. We set the parameters and press OK. A standard Windows file selection window opens. We look for the file mesh1 and open it. The program asks with what parameters to load the project. If you have previously performed simulations, you can use the previous settings. As we are learning, we will select the option No and load the program with the default parameters. We can already see our mesh. To rotate the geometry, you have to press the left mouse button. To scale, turn the mouse wheel, and if the right button is pressed, you can move the view. On the left, we can see a window with a list of our elements. In the tree, there are 3 sections: casting, mold, and empty. With the checkboxes, we can control the visibility of the elements. I will turn off the display of all the elements in the casting section. As we can see, for some reason, our casting remained on the screen, but our mold was deactivated. Why did this happen? When loading the mesh, the program still doesn't know which element is which, so the first element is assigned the casting parameter, and all others are moved to the mold group. The first thing we need to do is assign the correct structure. Assigning the structure is important because calculations such as filling, solidification, porosity, and hydrostatic pressures are performed only for elements of the casting type. For the mold, only temperatures and stresses are calculated. We double-click with the left mouse button on the element for which we want to change the type. In the window that opens, we assign the necessary element type. We press OK. A warning appears about resetting the boundaries to the default value. Since we have not yet set any limits, we click Yes and close the window. We repeat the operation for the second element. We turn on the visibility for our mold and set its type to mold. Done. Our elements now have the correct type. Now we need to specify the materials. We move to the Materials tab. Here we also see 2 sections: casting and mold. For obvious reasons, only one material can be assigned to the casting, and currently, no material has been assigned. We press the pencil icon for our casting. The Material Properties editing window opens. You can create your own material by pressing the New button and assigning all the necessary properties, but this is very complicated. For beginner engineers, we recommend using the materials from the database pre-installed with the program. We press the Import button. A selection window opens. The folder with the elements database is located here. We enter the folder with steels and assign steel of the brand GS45 for our casting. We press Apply and close the window. Now we move on to assigning materials for our mold. Unlike the casting, the mold can be made of many different materials, such as insulating materials, exothermic inserts, and other components. To assign different materials to different elements of our model, the program uses the concept of volume index. The volume index is a number related to a material that is assigned to each element. If we double-click on our mold, in the window that opens, we will see that it has been assigned the index with the number 1. I can change the index to any other. All indexes that are already assigned to the elements are marked in the materials tree with the symbol plus. PoligonSoft allows assigning up to 9 different indexes, or in essence, materials, to the model elements. To assign a material to a specific index, just press the icon next to the corresponding index number in the materials tree. We are going to proceed in another way. We will load not a single material, but a template of the technological process that contains all the characteristic materials of the technology being investigated. We press the 3 dots on the My Mold Materials line and select the sand casting template. Open. As we see, all indexes were assigned characteristic materials for sand molding. Now, to assign a specific material to our mold, we double-click on it and select the required material. In our case, we will assign the material under Index 3. By double-clicking on the material, we can see all its properties and change them if necessary. You can create your own materials lists and save them as a template for future use. Keep in mind that volume indexes can also be assigned to the casting. If I double-click on our casting, I will see that it has been assigned Index 2. The indexes for the casting do not affect the material. The material for the casting is always the same. These indices are necessary for performing specific tasks that are not covered in this lesson. However, it is advisable not to use the same indexes for the casting and the mold, as this can lead to confusion in later work. In previous chapters, we have defined the types of each element in our model and assigned materials. However, this is still not enough. For a correct simulation of the process, it is also necessary to define how the bodies interact with their neighbors. For example, our mold exchanges heat with the casting through its internal surface, but at the same time, its external part interacts with the environment. To define the heat transfer parameters between the adjacent surfaces of different elements, the boundary index is used. Let's start by going to the Modes tab. Here we see different display modes of our model. There are 3 modes: Type Mode, Index Mode, and Borders Mode. Type Mode shows which elements belong to the type casting and which to the type mold. Casting elements are shown in red, and mold elements are shown in blue. On the left are tools to control visibility. The red buttons control the visibility of casting type elements, and the blue buttons for mold type elements. I can completely activate or deactivate their visibility, activate Mesh Display, or display a section. Everything here is intuitively understandable, so we will not dwell on this. If we switch to Index Mode, we will see the volume indices, or in other words, the materials that were assigned to the different elements of our model. The mold is green because it has been assigned Volume Index 3, corresponding to silica sand. If we change the index, the color of the element will change and, as a consequence, the material it is made of. As the volume indices for the casting do not affect the material, I can assign any from the list, just to make it look prettier. Remember that the indices of the casting should not coincide with the indices assigned to the mold. Those indices that are already used in the model are marked with the symbol plus. Now let's switch to Borders mode. The model changed color again. Now I see 4 colors. Each color corresponds to a specific boundary index number. Boundary indexes are automatically assigned to all surfaces that interact in some way with neighboring elements. It allows setting the heat transfer parameters between the contact surfaces of different bodies. The gray color corresponds to Index 0 and is assigned to all surfaces of the tetrahedra within the bodies. If I activate the section display for our casting, I will be able to see that all elements inside it also have Index 0. Index 0 is a system index. We cannot control its properties. The purple color corresponds to index 1. It is assigned to the internal surfaces between elements of the casting type and elements of the mold type, that is, to those surfaces where heat transfer between the casting and the mold will occur directly. It is important to remember that if the internal surface of the mold is made of several different materials, for example, there are exothermic inserts, the boundary index for contact surfaces with properties different from those of the mold must be assigned manually. How to do it correctly will be covered in the next lessons. The orange color corresponds to index 17. It is assigned to the external surfaces of our casting. That is, to those surfaces where the molten metal exchanges heat with the environment. The blue color is index 18. It is assigned to the external surfaces of our mold. The boundary indexes, for now, only have an order number. No properties have been assigned to them. Let's fix this. We press Heat Transfer in the Main tab. To avoid having to set the parameters manually from scratch, we will again use the technological process templates. We select Import and find in the database a previously prepared template with typical boundary index parameters for sand molding. We open the file sandcasting.afo. As we can see, a list with 18 indexes opened, and each index was assigned parameters for a specific situation characteristic of sand molding. For index 1, the heat transfer parameters for the metal-sand pair were established. There also appeared indices with heat transfer parameters between the metal and exothermic inserts, coolers, insulators, etc. Index 17 corresponds to the metal/environment pair, and 18 to the sand/environment pair. As we have no other interacting surfaces, apart from indices 1, 17, and 18, no additional operations are required. We confirm the changes and close the window. Now we need to determine the orientation of the casting block in space. We go to the View tab and press the Reset Rotations button to set the default position for the coordinate system. For calculations, PoligonSoft assumes that the force of gravity is directed along the y-coordinate axis. After setting the default parameters for the coordinate system, we see that the y-axis is pointing upwards, and our casting mold is lying on its side. The simulation cannot be started this way for the simple reason that if we do not change the position of the mold, the metal will come out of the mold. To rotate our mold, we need to use the rotation buttons. To start, we need a sprue to face upwards, so we need to rotate the mold 90 degrees along the z-axis. We press the button. Done. Now the metal will be poured into the mold from above, but there's still something not right. Currently, we see a side view. This is not isometry, and in reality, we should not see the top surface of our mold. Let's rotate the system 90 degrees along the x-axis to understand what's going on. We see that during the design, the engineer used an incorrect coordinate system, so our mold is also rotated in relation to the y-axis. We correct this as well, using the step-by-step rotation buttons to set our mold horizontally. Now it seems to be straight. It is very important to use the rotation buttons and not rotate the model with the mouse. If we use the mouse, the model will rotate in relation to the three axes, and rotation along one of the axes will inevitably lead to displacement in the others. Visually, our model is already oriented correctly, but the axes of the coordinate system are rotated. To set the coordinate system according to the current position of the model, we switch to the Main tab and press Fix Rotation. We see that now the coordinate system is directed correctly. This is a teaching example where some errors have been made on purpose. In most cases, the coordinate system will be correct from the beginning. In the same way, we can change the position of the cutting plane. By default, the cutting plane is directed from the center of coordinates along the x-axis. To control the position of the cutting plane, we switch to section plane control mode and, using the rotation buttons, set the desired position of the plane. To move it along the axis, we use the push and pull buttons. To confirm the changes, we press Assign Section. Another necessary step for a correct simulation is to verify that our 3D mesh does not contain bad elements. We go to the Edit tab and execute the command Check Mesh Quality. The program considers elements with angles less than 6.5 degrees or greater than 175 degrees as bad. You can change the mesh verification parameters in the program settings, but we do not recommend doing so. Additionally, the solvers present a series of requirements for the relationship between the volume and surface area of the elements. These requirements are dictated by the numerical calculation method and cannot be changed. As we can see, some elements of our mesh do not meet the established requirements. If we close the window, we can see where these elements are located. In our case, there is nothing critical. We return to the verification interface and press the correct button. As we can see, all elements were automatically corrected. In case the program cannot correct the elements by itself, sometimes manual mesh correction is required, but that is already the subject of another lesson. Everything is ready to start the simulation. We press button Start Simulation and Parameters. To start, in the General tab, we need to set the initial temperature of the molten metal. We will set it to 1580 degrees. We will also configure the initial temperature of the mold to 20 degrees and the ambient temperature, which will also be 20. Here we also see the parameters that were set earlier: the materials of the mold and the casting, the heat transfer properties between the bodies. Additionally, we set the number of processor cores that will participate in the calculation. If you plan to perform calculations in the background and continue using the computer, you should not use all the available cores on the processor. You also cannot specify more cores than the processor physically has. In my case, I put the number 4. If any parameter is missing to start the calculation, it will be highlighted in red. To illustrate this, I will remove the casting material. As we can see, the General tab turned red. The casting material line is also highlighted in red, since without it the calculation cannot be started, so I return the material to its place. The parameter tabs that are displayed in green are configured and ready for simulation. The gray tabs are the disabled calculations, that is, those parameters that we are not going to calculate. In our lesson, we are only calculating solidification dynamics and porosity, so the flow, stress, and other tabs are shown in gray. The way to perform the filling and stress calculation will be covered in the next classes. Now let's switch to the Solidification tab. In the Enable Solidification model line, you can activate or deactivate solidification calculations. If I uncheck it, the whole tab will turn gray, meaning that this solver will not participate in the simulation. Next, we set for which elements to save the data, only for the mold, only for the casting, or for both. Then comes the calculation step line. This parameter is set depending on the process we are simulating. If the solidification process is very fast, then the calculation step must also be small. For example, for jewelry, we have a large and massive piece that solidifies for almost an hour, so a calculation step of 1 second fully satisfies us. Next, we set the step with which the data will be recorded in the calculation result file. For analysis, we do not need the same precision as for the simulation itself, so we recommend setting the recording step approximately 10 times greater than the calculation step itself. Finally, we must set the stopping criterion for the calculations. Here there are 3 options available. By default, the calculation will stop at the moment of complete solidification of the metal, but it can also be set to a specific time or stop when reaching a certain temperature. Now we move on to the Porosity tab. Here everything is obvious. We activate the parameters we need. We deactivate the Use New Macro Porosity Model option, as although the new model offers more accurate results, it requires quite complex configuration and a deep understanding of the processes occurring within the metal. We are not going to calculate hydrostatic pressure. Everything is ready. We can start our calculation. We press the simulation button and tell the program where to save the data that will be obtained as a result of the calculations. Our simulation has started. We just have to wait for the calculations to finish. The calculation starts as a console application, so if necessary, we can continue working in the program in parallel or just close it. The process is quite long. It takes several hours, so we are going to skip it and go directly to the analysis of the results. Our calculation has finished. To visualize the results, we start the Mirage module. In the upper left corner, we see 4 buttons that correspond to loading different types of data: temperature fields, porosity, pressure, and user-customized data. Let's look at the temperature data. We press the Open Temperature button and select the corresponding file. The file will have the same name we assigned when starting the simulation with a solid prefix. Our calculation is already loaded. At the bottom, we see buttons similar to those we used earlier to control the visibility of the elements. The red buttons correspond to the visibility of the casting, the blue ones to the visibility of the mold. I can activate and deactivate the visibility of the object itself, turn on the mesh, disable the visibility of the section, among other things. On the left, the familiar object tree, and buttons for precise positioning, rotations, standard views. There is nothing complicated here, so we will not dwell on this. On the right, the temperature scale. As we see, all values before solidification are presented as percentages of the liquid phase, and the values after solidification as temperatures. To better understand when solidification occurs, the liquidus and solidus temperatures used in the calculation are indicated on the color scale. Here, if necessary, you can create your own color scales or load previously prepared ones. You can also change a value on the scale itself. For example, concentrate its points in a parameter change area that is of more interest to you, or exclude some values from consideration. Let's launch the automatic playback of our simulation and see what conclusions can be drawn. By default, we see how the surface of our casting cools. If I am interested in the temperature at a specific point, I can set tracking using a control point with a double left click. To remove a point, we double-click with the right button. To remove all points, you have to press Ctrl D. The surface temperature is not the most informative parameter. To see the processes inside the piece, I have 2 options. The first option is to activate the visualization of the section. In this case, we will be able to see the temperatures not only on the surface, but also inside our casting. The position of the section is set in the same way as in the master module. We need to switch to the section control mode using this button, and then, using the rotation and displacement commands, place the section in the desired location. To confirm the displacement of the section, we press the Assign Section button. In this way, the dynamics of temperature changes within the defined plane of our casting can be seen, but this method is still not clear enough. The main objective of calculating the temperature field is to determine the places where thermal nodes form, which are areas within the casting that cool more slowly. As a result, cavities with molten metal are formed, while all the metal around the thermal node has already solidified. Due to the contraction of the metal when cooling, most shrinkage defects will form inside the thermal nodes. Let's do it. To switch to the thermal node display mode, we press the Cast Isosurface button. We are interested in places where the metal is still in liquid phase, while the metal around it has solidified. We set the value for the isosurface at 0%, which means completely solidified, and the option to show the isosurface and all values above. That is, only those places where the metal has not solidified will be shown. We start to review. At second 320, we see the formation of a thermal node in the sprue channel, but as it is outside our piece, it does not concern us much. We move on. We see the formation of multiple thermal nodes in almost the entire round part of our piece. And this is already bad. This is where porosity will form. In the end, we see the formation of a huge thermal node in the middle of our piece. In this place, a shrinkage cavity will almost certainly form. This example is made for educational purposes and has many errors from the beginning. For example, the total absence of feeders. But if we were investigating a real casting, we could confidently say that there is a guaranteed defect here, and the technology needs to be changed. Now let's specifically look at the places of porosity formation and the contraction pattern. To avoid closing the current temperature file, we launch another copy of the Mirage subprogram and open the file with a porosity calculation. When determining the places of porosity formation, PoligonSoft uses a complex algorithm that determines the places of formation of shrinkage defects and porosity. Macroporosity is formed due to insufficient feeding, that is, the lack of a necessary volume to compensate for the contraction of the alloy during solidification. Sometimes, the level of porosity can reach 100%, which means the formation of a shrinkage cavity. Microporosity is formed in the last stages of the casting solidification, when the gravitational flow of the molten metal through the dendritic network is no longer possible, and filtration flow becomes the only feeding mechanism. In the end, the data on macro and microporosity are combined, and we can see them as a porosity scale in percentage from 0 to 100. For clarity, I will activate the visualization of the section along the y-axis. The melt mirror is shown in green, but for this analysis, we are not interested, so we will deactivate the visualization. As we can see, we have two critical problems. Firstly, a noticeable shrinkage throughout the upper surface of our piece, which is quite expected due to the lack of feeding mechanisms for this area. Also, in many places, the emergence of porosity on the surface is observed, which is also not very good. Even at this stage, it is clear that the proposed technology is not suitable for obtaining quality casting, but let's see how the situation is with the porosity inside. Similarly to temperatures, we activate the isosurface display mode. To start, let's ask the program to show all the places where the porosity is greater than 2%. We see the presence within the pieces of areas with porosity exceeding the established threshold. If we reduce the porosity display threshold to 1%, we see that practically our entire piece has defects. The specific porosity threshold depends only on the quality requirements of the piece you are producing, so here you can choose any value. With this, we conclude our lesson. Today we learned to perform temperature and porosity analysis for our casting. We located the places of formation of thermal nodes, shrinkage defects, and porosity. In the next lessons, we will do a more complex simulation, where we will learn to correctly set auxiliary elements such as exothermic inserts and coolers. We will learn to calculate the dynamics of mold filling, as well as residual stresses and deformation. I hope you enjoyed this video. Thank you for your attention.